Hello everybody, Mr. Hasty here again. Today we're going to be talking about gas pressure, and this is an extension of 12.1. So, pressure is an amount of force per unit area. So let's try to get a rough idea of what pressure is and how we measure it. So for most things, for physical quantities, what we think about is if we have a certain amount of force, we can think of that as weight because we don't normally talk about force in here. Now, if we have a large area that we're putting that force on, and we have a small area we're putting that force on, the smaller area will have more pressure. This is why something that's pointy versus something that's blunt, with the same amount of force, this one creates more damage, primarily because all that force is centered into a smaller area, into a very, very fine point. So, the typical unit for measuring pressure is the unit for force in the metric system is a Newton. Now, we haven't dealt with newtons yet this year, but what a Newton is it's a kilogram in normal gravity. It's a kilogram in normal gravity. Now, we're not going to get too far into that, but if we think about 1 kilogram, about 2.2 pounds, in normal gravity, that's a Newton. And so that's how we measure force. We measure pressure. The standard unit that we oftentimes use is called a Pascal, named after Blaise Pascal, and it is a Newton per square meter. So if we had 1 kilogram in standard gravity on a 1 meter by 1 meter pad, that is a Pascal. In the English system, we say pounds per square foot or pounds per square inch, depending on our application. Now, oftentimes Pascal is too small of a unit, so we'll do the standard thing they do in the metric system, and occasionally we'll talk about kPa, which is a kilopascal, 1,000 pascals. And sometimes that's more useful to talk about. But that's pressure in a general sense. Let's talk specifically about gases. Here I have two different containers where the amount of gas, the number of particles is the same, but in one of them it's in a much wider area, creating lower pressure. The way gases create pressure is when the particles hit the outside containing edge, that is what we call pressure. That's the force. Now, each individual particle won't generate very much force, but all of them put together generate enough force that it can be measured. So if we crunch those particles into a much smaller region, it increases our pressure. And the reason for that is, imagine if you had the forces distributed over a much larger area, we have lower pressure. But if we make that area much smaller, we have much higher pressure. Now, one of the tricky things about talking about pressure is just the sheer amount of ways that we have to measure it. So the next thing we're going to discuss is the measuring of pressure. So the first unit we talked about, units and scales, we talked about a Pascal, which is 1 Newton on 1 square meter, and its big brother, the kilopascal, used for measuring higher quantities. There's also other methods. So one of the first methods was that used by a barometer. A barometer is a device used to measure atmospheric pressure. So that is the pressure of the gases in the air around us in our atmosphere. It was developed by Evangelista Torricelli, and this is an example of a barometer. So the liquid inside of there is mercury, and this part is open to the outside air, and at standard pressure it will push the mercury up the tube. Standard pressure is 760 millimeters. And when they say millimeters, millimeters of what? It's millimeters of mercury in the tube. So we actually have a way of measuring pressure as millimeters of mercury. And we'll say for barometers especially, mmHg. Standing for millimeters of mercury. Now there's also a manometer, which is a similar device. It's used to measure gas pressure in a container. So we have one of these down here. And here's the atmosphere coming in. And here's the gas that we're measuring the pressure of. And if the gas on the inside and the atmosphere on the outside have the same amount of pressure, it'll be equal as shown in the diagram. But let's say the gas has more pressure than the atmosphere, it will start to move the mercury up on that side and down on that side. And we can measure things similarly in millimeters of mercury. Now, in addition to that, what is oftentimes useful is, units and scales, we have pascals and kilopascals. We also have millimeters of mercury based on our use with barometers and manometers. We also have an atmosphere. And an atmosphere, abbreviated ATM, is 101.3 kilopascals or 760 millimeters of mercury. And that's the reason it's called an atmosphere is because that's considered the standard pressure that Earth's atmosphere is. Of course it varies, it goes up, it goes down, but that was kind of set as a standard. So we have another unit, we have atmosphere. In addition to that, there's pounds per square inch, there's bar, which is another measurement, there's torr, which is another measurement. We're not going to mess with bar and torr very often. We will mess with pascals and kilopascals, millimeters of mercury, and atmospheres. Now, if you ever want to convert between the two, on page 407 of your text, there's a table which shows that 1 atmosphere is equivalent to 101.3 kilopascals, which is equivalent to 14.7 pounds per square inch, and so on. So there is a table to reference all these. So why are there so many? Basically because there's different devices and different techniques that people have used to measure gas pressure over time. Every time a new device is created or a new method is created, it involves the use of a new scale, a new unit, something along those lines. So, one of the important things we have to understand is that there's a standard pressure number that we use. The standard pressure number we use is 1 atmosphere, or 101.3 kilopascal, or 760 millimeters of mercury. All three of those are equivalent, just like 32 degrees Fahrenheit and 0 degrees Celsius are equivalent. And so any of those can be interchanged, and they're what we call standard pressure. So now we're going to talk about pressure with mixtures of gases. So Dalton's law of partial pressure, and Dalton's law of partial pressure says the pressure of a mixture of gases is equal to the pressure sum of all the gases. So let's say we have two gases. The pressure, the total pressure, is equal to the pressure of gas 1 plus the pressure of gas 2. If we had 3, we'd say plus the pressure of gas 3. And we would just keep adding pressures on until we had as many gases as are present. So let's give a real quick visual of this. So let's say that we have a container, and assume these have lids, and in this container is gas A, we'll label it A, and it has 5 particles, very small sample. It's going to have a certain amount of pressure. And we have gas B. We're going to draw these using squares. And there's 4 of those. Pretend these are good squares. And that's going to have a certain amount of pressure. And we have another container of gas C. And it has triangle shaped gas in it. And it has 5 of those. It's going to have a certain amount of pressure. And if we add all those together, we're going to get a container. I'm going to make it slightly larger. Pretend like it's the same size. It's supposed to be the same size. With 5 circles, 4 squares, and 5 triangles. And it's going to have a lot more pressure because it's got a lot more particles. And the actual amount of pressure it's going to have is just the sum of each of these individually. So you add up the pressures to get your total pressure. So let's look at an example. A mixture of oxygen gas, that's O2, nitrogen gas, N2, and carbon dioxide gas, CO2, has partial pressures of 0.15 atmospheres, that's what ATM stands for, 0.12 atmospheres, and 0.70 ATM, respectively. So this word respectively, in case you haven't ever used this before in a problem, it means they're in the same order. So the first gas listed was oxygen, the first measurement listed was 0.15. The second one listed was nitrogen, the second one listed was 0.2, so that's our nitrogen, 0.12, so that's our nitrogen. And the third one listed is carbon dioxide, so we have 0.70 carbon dioxide. What is the total pressure of the mixture? So in this case, we have 3 gases, so the pressure is just the sum of the 3 gases, 0.15 plus 0.12 plus 0.70. We add those together. They're all in atmospheres, and we get 0.97 atmospheres. Now, it's that simple. You just add them up. It doesn't matter if those measurements were in atmospheres, pascals, millimeters of mercury. It's going to work out like that. The other thing we have to keep in mind, though, is that for sig figs, it doesn't affect here, but the rule for adding with sig figs is smallest number of decimal places. And so in this case, it works out because all of them have 2 decimal places. So our answer should have 2 decimal places. All right, let's look at a slightly more complicated example. Carbon dioxide is mixed with nitrogen and argon. If the total pressure of the system is 30.4 kPa, that's kilopascals, the partial pressure of nitrogen is 3.7 kPa, and the partial pressure of argon is 3.7 kPa, what is the partial pressure of the carbon dioxide? So in this case, it's simply wanting us to solve for one of our gases. So if we have the pressure is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas. It says our total pressure is 30.4. It says we don't know the pressure of our carbon dioxide. So we're missing one of our pressures. But we know that the other pressures are 3.7 and 3.7. So simply we combine like terms on the right and we get 7.4. And just like any other algebra equation that looks like this, we subtract on both sides. Now making sure to, even though that 4 minus 4 is going to zero out, we need that for sig fig purposes. We're going to get 0 and then 23, so 23.0 kPa. Simple as that. All right, guys, that's it for our discussion of pressure. This is going to come back later in other sections, and so it's an important concept for us to get down. All right, see you guys next time.